So here's another problem that's probably going to be best solved by conjugate beam. Again, you can see we're looking for slope and displacement at the midpoint, a specified point, so probably that's going to help out. Also, you'll notice that although this is not a horrible problem to do by direct integration, it would take some time to solve all the equations necessary, and then to go back and do some calculations. So I think, again, conjugate beam is going to be the best approach to this. You'll probably start noticing that just about any time you have point loads and you're worried and you're concerned about slope and displacement at just a point, conjugate beam is going to be your best bet. So how will we start this? Well, I need to draw the what first? Yeah, I need the moment diagram. And to do that, I need my reaction. So I'm going to assume that I have positive shear at A and positive shear at B. I'm going to kind of slide this over to the side a little bit. I can't do this one off in the well, I guess I could do it. Let's see. It's going to be, the reaction at B is going to be negative. And it should be 45 divided by 12. What's 45 divided by 12?
3.7.
3 point what?
7,000.
And then, of course, the reaction at A would be 1.25. I did that kind of quick, but you could check that. I just pretty much did them in my head. I figure at this point in the course you could probably do those. So we'll just kind of skip through that quickly. And now I'll draw my template so that we can construct our shear force and bending moment diagram. So typically we define our positive x-axis and positive shear. All of our units will have kips. So what's the shear at A? Looks like it's 1.25. The change in shear is the area of the load curve, which is 0, so I stay 1.25 with a 0 slope. Then I drop 5, which brings me to negative 3.75. No change because there's no load, so there's my shear diagram. Again, at this point in the course, you're probably pretty comfortable with that. So let's draw the moment diagram, the component that we actually need. So there's my positive x and positive moment. And again, I'll have units of kip feet. What's the moment at A? 0. And the moment at B is also 0. So the change in moment is the area under the shear diagram, which is base times height. The base is 9 times the height, which is 1.25. 11.25. Thank you. I was just going to ask for that. Of course, the slope is given by the shear. The shear is constant, so I have constant slope, and it's positive. And then, of course, the change in moment is the area into this part of the curve. So that would be base times height, 3 times 3.75. I'm pretty sure that's a negative 11.25. That brings us back to 0. The slope of the moment diagram is given by the shear. The shear is constant, so I have constant slope, and it's negative, so constant negative slope. So there's my moment diagram. Any questions about that? Again, in terms of moment diagrams, that one's pretty straightforward for what we've been working on. So let's come over and construct the conjugate beam. So how do we construct the conjugate beam? We look at our support conditions, our connections, and we see what we have. So this external pin in the real beam is going to be what in the conjugate beam?
External pin.
The same. Then there's nothing here, and there's another one. So our conjugate beam looks pretty much exactly the same in terms of the geometry. So I'll still have a pin and a roller. Now I'm going to apply the moment as load. So I'll do that. So again, I like to just sketch the moment diagram right on the beam. I know that value is going to be 11.25 kip feet, and of course we're going to divide it by E and I. Now, this moment is positive or negative? Positive. So it means it's going to be positive load. Positive load is up. Let me put some dimensions on there just to remind you. So this section is 9 feet, and this section is 3 feet. Now, the problem is asking for the displacement and slope at the midpoint. The midpoint's right about here. That's going to be 6 feet. So if I were to cut the beam about at the midpoint, 6 feet, what side of this structure would you like to work to find the internal shear force and bending moment? The left side or the right side?
The left side.
Yeah, I think there's a clear choice. The left side is going to be the better of the two. So that means to work the left side, I'm going to need the reaction for the shear at A. So let's make sure we get that first. So I'm going to assume at A, I have, here's my positive shear at A. So I'm going to have to first find that reaction in the conjugate beam. To do that, I'm going to have to take care of all these forces. So first, I'm going to have one force, I'll call it F1 for that triangle, and a second force, I'll call it F2 for that triangle.
That's pretty hard to see.
Is it changed colors? I'll go to purple. How about purple? All right, so what is F1? What's a triangle? So it's going to be 1/2 the base, which is 9 feet, times the height, which is 11.25 kip feet, divided by EI. So what's that value?
50.65
50? 50? Point what?
625.
Oh, that's a lot of decimals. I'll play along. There's kip feet squared divided by EI. And then F2 is also a triangular area, so that's going to be 1/2 base, again, times height, 11.25 kip feet divided by EI. What's that?
16.875.
16 point what? 875? Everybody else getting these values? Okay. So now what I'm going to do is come and sum moments about point, I didn't label that. That's point B and this is point A. About B. Now why am I choosing B? It's because when I sum moments about B, I should be able to solve for my AY reaction. And I want that because eventually I'm going to work the left-hand side. Now both these forces, F1 and F2 about B, create what kind of moment? Positive or negative? Negative. So I'll just start with F1, which is this bigger force, the 50.625 kip feet squared divided by EI. So that's the force. What's the moment arm from B? Well, it's 3 feet, and then how far from here to the centroid of the triangle? 3 more feet, right? So that should be 6 feet total. And then minus F2, which is 16.875 kip feet squared over EI. And what's the distance from B to that centroid?
2
feet, correct. And then I get to AY, or the shear at A, and that's going to create also negative moment. And what's its moment arm? 12. So solve for the shear at A. It looks like it's going to be negative. You guys will have to help me with that. 25, 6, 27, 28, something like that. I'm guessing. You shouldn't be guessing. You should be calculating.
28.125.
28.125. Anybody else get that?
Yeah, negative 28.125.
That does not sound bad. I like that. So that should be kip feet squared divided by EI. Any questions about that? All right, so now I'm going to draw this free body diagram here. I'm going to draw it down here in the bottom. So what I have is my beam. It's 6 feet long. I've got my reaction, which is actually down, and that's equal to 28.125 kip feet squared over EI. Okay. I've got my internal shear at the cut. There's the positive of that, and I've got my internal bending moment at the cut. I also have the load. So the distributed load I know is acting up. What's the value of the load right there? Well, I know it's 11.25 here. That's at 9 feet. So a similar triangle should tell me that if it's 1.25 to 9, what should it be for 6? It should be 2/3 of that. You said it's what? 7.5? 7.5? So that should be 7.5 kip feet divided by EI. Does anybody have any questions about that?
Why is 7.5 again?
Maybe the easiest way to draw it would be I'll piggyback over here on the diagram. So similar triangles, right? So I know the height here is 11.25 to the length, which is 9. So this triangle is similar. So the height here, H, should be proportional to 6. So if you solve for H, you should get 7.5. Another way to do it would be just to find the slope of the line, which would be 11.25 divided by 9 and multiply it by 6. And that's pretty much what you see here. Okay, so Mr. Griffin didn't like my orange color. I'm switching to purple.
I don't like Tennessee here.
We don't like Tennessee anywhere. Not just here. Sorry, Mr.
Hey, I bought these colors long before I moved here, so this orange doesn't count.
I would think from where you were, orange would be a good way to end up in the river. Anyway, on to other things. So what's F3? It's the area of the triangle, so it'd be 1/2 base 6 times height 7.5. I'll squeeze that in down here. So F3 is 1/2 base, which is 6 feet, times height, which is 7.5 kip feet divided by EI. What's that equal to? 22.5. That's kip feet squared over EI. Lots of little details to keep track of. So now I've got everything put together. It's just a matter of finding the shear force and the bending moment. There's no particular you could do either one. I'll do the moment one first. So I'll come up here and sum moments at the cut and set it equal to 0. So I'm using right hand rule, so this moment is a positive moment. What is F3? What kind of moment does it create? Positive or negative?
Wait, about the cut is negative.
Negative. So it'll be negative 22.5 kip feet squared divided by EI. And what's its moment arm to the cut? 1/3 the distance, 1/3 of 6 is 2. Then I have the reaction force, which creates what kind of moment about the cut? Positive. And that is 28.125 kip feet squared. Again, divided by EI. And what's its moment arm? 6. So you should be able to solve for the moment.
Negative 123.75.
Say that again, Mr. Rippey. What?
Negative 123.75.
123.7. Does anybody else get that? So 123.75?
Yes.
And that should be kip feet cubed over EI. Any questions? Anybody else having problems with getting that value? Pretty small number relatively, because that 123 is going to be divided by E, which is huge, and I, which is huge. So we're going to have a very, very small displacement. Also, I've had people in the past ask me, after they see all this divided by EI, divided by EI, divided by E, can I just divide by EI right here and be done with it? You can. The problem is what's 11.25 divided by EI? It's incredibly small. And you'll probably round something off, and it'll just lead to the net. You'll end up writing a very, very small number a bunch of times. So I find it better just keep your EI, hold on to it, and wait till now. Because we know that the displacement at the midpoint is given by that moment, which is this value, which is negative 123.75 kip feet cubed. And now we just have to do our unit conversion. So again, we're going to divide by E and I. So E in this case, again, is 30,000. And that's kips per inch squared. I is 800. And that's inches to the 4th. And then we have to convert cubic feet. So that's 1,728 inches cubed and a foot cubed. And if you check all your units, kips cancel, cubic feet cancel. You have inches to the 5th over inches to the 4th, which is just an inch. So what's that value?
I got 0.009.
Anybody else get that? 0.00 what?
9.
That's close enough. 9/10,000ths of an inch. That's pretty light. Now, think about it, though. This beam's only 12 feet long. If you count 12 tiles on the floor, that's how long this beam is. Pretty short. It only has a load of 5,000 pounds on it. That's barely a car. And it's made of steel, and it has a beam with 800 inches to the 4th moment of inertia. That's pretty hefty. So it makes sense that it would have very little displacement. I'm going to try to squeeze in down here the remaining part, which is we need to sum the forces to find our shear value, which of course maps to the real beam as the slope. So looking at our diagram for shear, I've got the shear force acting down. I've got my load 3 acting up, so that'll be plus 22.5 kip feet squared over EI. And then I've got my 28 acting down. This is going to be even smaller, a relatively smaller value. So the shear is going to be equal to what? Like 5 point something? 5 point what, I'm sorry?
625.
625. That's a relatively pretty small value. I've run out of space, so I won't be able to do the direct conversion, but we can go ahead and divide by E and I, and then of course to convert to to square feet, we'll have to multiply by 144. So take this value, multiply it by 144, and divide it by E and I, and what do you get? Probably a bunch of zeros. So that's 4 zeros. And then 3 what?
3.38.
3?
Yeah, 338.
Oh, let's make it 3.4. That's pretty small. When you say that's pretty small? And that's going to be radians. Yeah, go measure that. I'll subscript that book title, Good Luck. So any questions about that? That's very doable. I think that took us 22 minutes, but I tend to elongate some of the stuff. Other questions?